Hi everyone, I'm Shahoei from Paul's Children's Lab, and my lab is basically, our lab, is basically interested in simulations and computational study of large biomolecular systems, and we basically use MD as like the primary method. So you'd see, what is it? It is this protein insertase that comes to the help of the ribosome to insert transmembrane proteins into the lipid membrane. I know too many words were there. If you bear with me for a few seconds, I promise it will be like crystal clear. So basically, let's have a quick review on what ribosome does. It's basically this protein synthesis machinery in the cell. It translates the genetic information into proteins. All right, so here you see in the green is the large subunit. In yellow, you see the small subunit. Small subunit is basically the decoding center, it's the decoding part of the ribosome. The large subunit is the catalytic part. You see the mRNA here. Those dark greens that you would see here, and in the GIF I'm going to play, are the tRNAs, which basically deliver the amino acids to the ribosome. And any light blue particle you would see is a protein that does not belong to the ribosome, but does help the ribosome in the whole translation process, and in this case, in inserting the protein into the lipid membrane. So here you see the assembly of the ribosome. tRNAs are basically coming to the ribosome with the amino acid. Here you see two basically elongation factors. This big one is EFG, if you're familiar with, at least in the bacterial case. Those small ones that carry tRNAs with themselves are elongation factor TUs. You see the nascent protein is growing, elongating like one amino acid at a time, going through what is called basically the nascent protein exit tunnel of the ribosome, and now it's about to exit the ribosome. But you don't want the nascent protein just released in the solvent. That interesting particle you see there is called signal recognition particle. It realizes the nascent gene has to be basically rescued, and then it accompanies the ribosome to the translocation. This protein you see here in the membrane. This is basically a membrane insertase. This is what, for example, you'd see is. All right, so our lab has been and is working on at least 3 of these systems. You'd see is here. So why we have been studying it extensively for the last 1 decade almost. And this is holotranslogon. And you see interesting substrates these proteins do have. You'd see specifically, if you're familiar with Atp Synthase Structure, so basically it has this transmembrane part, and in that it got the C ring. You'd see basically is in charge of inserting the C ring into the membrane. For the whole subunit of Atp Synthase, you need holotranslogon, which we are starting to work on. And say why one of the interesting nascent proteins that it in this case inserts and secretes through the membrane is bacterial Ribosome. Let's take a closer look at you'd see. It looks like innocent, just like very simple, 5 helices. Yet the simplest case basically took over 3 decades, I believe, for us to figure out the structure. So what our lab did last year was we had these beautiful cryo-EM maps from our collaborators' lab, Roland Beckman and Munich. And we started with homology modeling. So what you see here is what homology modeling gave us. And then we used this method called molecular dynamics flexible feeding, MDFF, which was developed in our lab to basically drag the helices into the EM map to get the basically the functional state. That's basically what MDFF is for. You start the structure, whether you got it from homology modeling or X-ray, and then you want to have a functional state. That's what we do all the time with ribosome. This is a very smaller case. And then you'll end up with having an all-atom structure, but in the functional state. A few months later, the crystal structure was out, and we got really excited. It was in agreement with our structure, and we got even more excited because it didn't exactly agree with our model, because what we proposed basically was a ribosome-bound EC, not like an X-ray EC actually wouldn't be in a physiological state. We took another step. Basically, we predicted the site, the position of the nascent chain, because in the early cryo-EM maps we didn't have those. And then our collaborators confirmed. So we were really excited. And I told you all about the structure almost. Now it's about the function. So we couldn't talk about function at all before we had the structure. What we speculate happens is, what is the role of EC? So you look at the EC substrates, they all have hydrophilic and terminals. So obviously it's not possible for a hydrophilic chain, for a hydrophilic tip to go into the membrane. That's why you need something like EC to facilitate this whole event. So, for example, this FOC ring, it has like charged amino acids on the tip, then it has this hydrophobic region, and then again hydrophilic for the rest. So what we speculate is happening is, on top of EC basically, you have this hydrophilic region, which some people call it water well, here shown in blue. So basically what we think happens is the interactions between this hydrophilic region on top of EC with the tip of the nascent protein drags the nascent protein in, at least for the very initial stage of the insertion. And then interaction between the rest of the nascent protein, which is hydrophobic in nature, with the rest of the EC, which is hydrophobic as well, would take care of the rest of the insertion. All right, how can we test that? So, as someone who has been always interested in the function of ribosome, I thought we can't get reliable results without incorporating the whole ribosome. So I thought, okay, we add the ribosome, right? And this was 9 months ago, and I've been working on this for like the last 6 months. That's why I'm showing you this ugly movie, basically, yet I'm so proud of it, because finally, very recently, I got the whole model, like 3.9 million atom stabilized. And yeah, I didn't get enough time to make a good video, but I took away the water molecules, so you see the magnesium ions. Those familiar with ribosome know how crucial the placement of those ions are. It's very easy to get the ribosome blow up in the simulation, and you're hearing it from someone who has done it multiple times. You have to calculate basically the electrostatic potential. It's very negative, right? Because 2/3 of the ribosome, after all, is nucleic acids, so RNAs, and then you have to sometimes even place those. I guess in this system, at least I have 9,000 magnesium ions, and here we go. We have reminding ourselves what we wanted to do. Basically, it was, what does EC do? How does it facilitate the process? So here on the left, basically, I have the nascent protein just about to interact with EC. On the right, I have the final state. EC already inserted into the membrane. You're a modeler, you look at this, you can't help it. You would think of stirred molecular dynamics. So basically, the goal would be saying how we can get from this state to this state and what we gain in this process. Parallel to this, another grad student was working basically on the steering protocol. In the absence of ribosome, we wanted it the simplest case possible to begin with. So now we have the steering protocol as well, and we have the other complete ribosome model. And what would be the next step, future step? Putting these two together and see what happens, basically. So these two steps, you can basically calculate the free energy differences between these two, and the difference would give you basically the cost of insertion of the specific substrate. And then you can see, okay, how EC is facilitating this, And hopefully, how is it basically selective? This would be the ideal case if we can find out how selective YTC is as a function of the sequence of the protein. We basically did something similar with SegWi, so I'm hopeful about it. Time's up. Conclusion very quickly. We predicted ribosome-bound YTC. There was no ribosome back in the day, back in the time, but there was cryo-EM. And then we built a whole model. We have the initial and final cases. We have the steering protocol now. All we have to do is transition path sampling and free energy calculations, and hopefully we'll realize how YTC works. And thanking the resources, my advisor, Abby, the postdoc in our group, who is extremely helpful. Thank you.
Okay, we have time for 2 short questions.
In your the last one, suggested protocol in the simulation, what is happening in the PTC? I mean, what do you treat about protein synthesis in simulation? In PTC, peptide transfer center, in the center of the ribosome. I mean, yes.
You got it. Okay, so basically, yeah, you have a length of the ribosome, and after that you have like about 7 or more nascent chains, and you change those in the peptide transport. It's the model part.
Okay, so in the simulation, no additional amino acid synthesized.
I mean, you can't get that with MD, right?
Yeah,
It's
yeah.
like one, yeah, it would be on 10th of second time scale. No way you can get that.
Oh, we have one in the back.
So why did you use like a truncated ribosome, since of course ribosome is very large and very difficult to simulate? Why don't you use like a truncated, just PET, similar to what that was done in the SegWi project, and have some small peptide chain trying to drive through?
We did that back in the day because we couldn't do a full simulation. Now we can't. We have the resources, we have the techniques, we have the method. Why not? That would be like basically the answer. But then also we know we get some side effects when we truncate the ribosome. I'm not a biologist, but biologists, collaborators keep telling me sometimes, like even when you are dealing with a nascent protein that is exiting the ribosome, you might have proteins from the small subunit doing stuff that would be important. So if you can do it, why not? But in SegWi case, yeah, it was, we really couldn't afford it.
Okay, let's thank the speaker again.